With Chunming Lee, and I'm now a practical architect and was working as a research assistant in the University of Hong Kong. And I'm here today to present a cooperative research project with Dr. Kai-Cong Wu. He's an assistant professor at the University of Hong Kong. And this project explores an innovative approach to digital additive timber log design and fabrication workflow, featuring an initial timber log joinery system. And our research began with explanation of a previous study made by researchers in this field, including their method and limitation. We then turn our attention to the natural property and the characteristic of the material itself, observing its behavior and potentials. Our initial findings have led to an invention of a new joinery and the development of a novel algorithm, which we will present and explore in greater detail throughout our research. I would like to show two cases demonstrating the research in timber logging field. Researchers are exploring the potential of timber natural shape in design feature remastering and structural performance. By studying the characteristic of rule logs in various shapes, they develop the design possibilities that can be applied in different contexts with unique design feature. However, the limitation work with rule logs are becoming increasingly obvious, including the replication of design feature and structural performance. In comparison, the log neck project, which based on a bottom-up project logic, is particularly challenging due to the shape of the material and be more spontaneous upon the material nature shape. And in another project, the material are not very well aligned with the neighbor elements. In terms of efficiency, the use of robotic arm for complex joinery provides stabilities and accuracy during the installation process. However, this approach also can be time-consuming and may not be suitable for low-tech traditional craftsmanship, which is commonly used in real-life construction sites. Our previous researches are being limited by need of high construction accuracy and use of sophisticated machinery, result in inflexible, slow, and non-recyclable designs. In contrast, our method aims to achieve material simplicity and convenient processing with minimum requirements of equipment. This approach not only aims to achieve the alignment between digital design and the physical model, but also efficiency in construction process. Additionally, our design philosophy emphasizes the maximize the axial alignment, which take advantage of material nature strengths property and result in structural efficiency elements, and aim to strike a balance between efficiency and accuracy, allowing the faster and more flexible installation process while still maintaining the requirement of precision. Based on the timber axle performance feature, this joinery prototype was designed to allow elements A and B on each side to rotate independently while maintaining the structural continuous. This design enables the timber elements rotating without compromising, and their structural elements providing enhanced flexibility for overall structures. This method section consists of 3 parts, including data site, algorithm, and prototype testing. For the system overview, the input is data site for the branches geometry and guiding shapes, which are used to drive the algorithm. The black box algorithm integrates rules of rotation and alignment with evolutionary computing tool, constant of Wallasey, and Galapagos in Grasshopper. The output is a site of a customized fabrication detail and assembling solution that can be used to constrain the desired structures. The data size of branches will set up firstly with branches and forks, abstract and purging them to either I shape and Y shapes. Animation on the right side showcase the direction potential that cutting the branches at various positions, even within the same forks. This demonstrates the fabrication possibility to meet the design feature, providing more options. Use this animation, you can evaluate different cutting position with the same forks to achieve desired design feature and performance. Here is a recording of arch prototype digital assembly. The whole arch elements are considering in the same time from one side to another. With each placement, there is 3 levels of freedom. Branch selection chooses suitable branches from the dataset to form the framework. Orientation angle, optimize the angle of the branches to achieve better structural performance. And also treatment positioning the treatment and effects the ending direction and stability. The single curvature system was upgraded to a truss-like shape to enhance action's performance. The system will also testing with a multiple related geometry guiding. Additionally, the prototype used 2 categories of law, including I-shaped branches and Y-shaped forks. I-shape will form the mainstream column, and the Y-shape will are the secondary columns. After the arch test, we conduct an experiment involve an triangular door guiding by surface geometry, which allow us to further access the feasibility of our system design in a more complex scenario. For the triangular system, the input and outcome is similar with the previous ones, and the income including a form-finding framework based on the context. The library of Y forks will be set up firstly, and the flexibility of each replacement will be considering as a branch selection, treatment position, and rotation angles as well. The computation follows the physical logic, starting from the lower framework units, and sequentially, the system will use the generated ones as an existing condition to generate the middle unit, layer by layer. Yeah. The target, the target triangle can be modified based on the generated ones. If the endpoint of the branch does not match the target points, the generated point will become the new reference point to in the following computation to minimize the deviation. The result will including the cutting position blocks within fabrication. This information can be marked on the materials, which will allow a simple trimmed treatment, which helps the new joinery, with the help of new joinery, installation requirement can be met with a simple flat trim. Yeah, with the computation, we have multiple solutions based on the same branch selection and treatment. This will provide us with options. Solution, the first one is a solution with minimum value can help to reduce the transportation difficulty. This is because the material will occupy less space during the transportation. Second one, the flat solution can access in the on-site assembly. This is because the shape is easier to manipulate on-site and require less structural supporting during the construction. Third one is optimizing of both solution, minimized value, and flattened shape is possible. This workflow will potentially maximize the benefit across not only the design, but also transportation and the assembling stage. And this method can be also demonstrated on the specific site in a large scale, incorporated two prototypes, namely trusses and surface, with the primary structural elements designed according to the trusses arch logic, and the envelope also shaped by the surface guiding logic. Yeah, basically this is the ending of the presentation. And please connect us with if you have further questions. Thank you for listening.